So, have you guys ever taken a look at Ramsey's previous videos? Good, then I'm done. I'm kidding. Okay, so I think for the sorry for the bad joke. But after all, for this project 4A, I think it's relatively simpler. Um, and for 4B, it's also simpler than P3B, assuming you've learned something from P3B. So I think I would not spend too much time. Um, you know, yeah, I will surely go through this two projects, two parts, but I think I'm not gonna as deep as I did in last time. So let's first start from P4A. So this is like the real application that you learned from class. So basically, we use the condition variable to handle the like multiple threads in a real consumer producer model. So I think you've already taken had some time to look at the code frame, right? So there are a couple of like the client, so some request.c, so none of which you need to really understand. So all you need to do is just in server. So you need all I think all your updates or modifications happen here. Um, you should, if you are interested, you can take a look at like client.c. These are a bunch of there are several methods that handle the socket to handle the HTTP request, but you don't need to care too much about it. So all you need to do is take a look at server here. So this is the code frame we have. So in main, we basically first handle the input, right? Because according to the specs, we have like feeding several parameters like the port number, uh, number of threads, and buffers. So these are, I think, very straightforward, and you can easily do that using like here in this method. And after you parsing the input arguments, then you basically will create some threads, right? So the number of threads is essentially the parameters you get from the input. So by creating threads, I think it's very straightforward. You use the p thread underscore create, right? This API. I think you've seen it many times in the lecture, both in the lecture and worksheet. And after that, you will see that we enter basically a while loop. So it's very like in P3A, right? You in the server, you have a while loop, and you iteratively wait for uh, the request, and then you handle that. But here because we have like created multiple threads to handle this, so right now when we do the request handle, it's no longer happening here. The reason is that if we don't have multi-threads, we only have one thread, which is the main thread, then we definitely, as a server, we handle it in a while loop, right? But since we created multiple threads, the real thing is no longer happening here. The reason is that you can just treat this whole project as a consumer producer model, right? So who is consumer? Who is producer? No one has an idea? So I think for the consumer, it should be like the request handle, right? Basically uh, take this count. This is like a file descriptor, but it's connection file descriptor, and then it handles the request. So basically, this should happen in your consumer method. And for the producer, essentially, it's just you put. So I think I can open. This is our in the textbook, right? The old model of the consumer producer, the very classic model here we've learned using condition variable. So as I said, in the consumer, you basically so yeah, here we actually maintain a queue, right, or a buffer, right? So we in consumer we basically get some values or items stored in the buffer or the queue, and then after we get this item in this simple model, we just print something. But in this real application, we'll basically do like the handle the request, right? So remember, because request handling is like can take arbitrarily long time. It's not I mean it's user defined basically. So you should definitely not put this request handler within this the log or the condition variable, right? You have to you just get this the item or the conf file descriptor, and then you handle that after the lock, basically. This is what consumer does. And for producer, it's kind of reverse way, right? You basically, if you see, okay, now currently the buffer is full, right? You can no longer put anything there. You just put this color to sleep using count wait. Once the buffer, there are some available slots in it, you basically store the current file descriptor into this buffer, and then that's it. So basically you follow this model and understand who is doing the producer, who is doing the consumer, and I think you're ready to go. So I think this project is is probably the easiest of the 5. I mean the part A. So even easier than the P1A, I assume, because I think you've already had this model, right? Sorry. You've already has this well-defined model. So you just follow this prototype and then filling everything necessary into it. And then I think you are ready to go. So I think that's it for this part. So any questions? Because I think it doesn't take much time. I think for this part, it really only takes like 2 or 3 hours, and that's it. And by the way, for this particular project, we don't have any hidden tests or any linked test or any Vagrant test. So good for you. Okay, so if you guys don't have any issues, then probably I'll jump in P4B, although it's easier than P3B, but still there are a couple of more important things to do.
You're telling me that I should just switch with my partner and take P4A?
Yeah, I mean, the normal strategy where two of you, one is doing A, the other is doing B, probably does not apply for this project, because I think it's not very well balanced. I mean, yeah, the workload for A is much lighter than B, so probably you should work together on B, and then yeah, probably one of you can work on A, because it's like 2 or 3 hours work. Yeah. Okay. So for P4B, again, we provide you another base code, which is different from the previous XV6 code. The reason is that, as we mentioned in the instruction, we used some the memory layout. So the memory layout, yeah, for this time I draw it explicitly here so that you don't need to look at the video again and again. Yeah, but I think hopefully it should be clear enough. So yeah, I can go through this memory layout. So this is the diagram that we have. After you implemented the thread, this is what the memory layout look like. But before you do that, according to the base code, you don't have this, right? All you have is the first 2 pages that is free or unmapped. This is the same with P3B. And then the code plus data for 1 page, and then the heap growing upwards. And they are all the same in P3B, right? And now we have a stack moved at the user top. And the difference from P3B is that now the stack for this process is only 1 page. It's fixed. It will not grow. Right? This is a difference from P3B. Instead of growing, we will basically put new stacks for the new thread downwards, basically. And we will have 1 page, every other page of guard page, which is free. The reasons that I think I mentioned here is that we want to protect, prevent stack overflow, such that say if a thread is doing very heavy recursion in this stack, right, and it will exceed this fixed size of 1 page, if there's no a guard page here, then it will cross over this line and enter the stack of another thread, which is bad, right? We don't want that happen, so we will have this guard page such that when the stacks is overflow, then we will raise a page fault. Okay, this is the purpose of the guard page here. Yeah, this is basically what the virtual memory layout look like after you implement threads. Okay, so let's take a look at the base code here.
So every thread has its own guard page beneath it.
Right.
Not just above the end of the stack. But
so yeah, you can do the math here because I think we only have 8 threads maximum. So each thread has got its own guard page. So it's basically 16 pages. And the stack of the main process has also got 1 stack and also 1 guard page. So in total, there are like 18 pages. Yeah.
So have you guys already done putting the stack at the top? Like you've already in the XP6?
In the base code we provided you guys, we have already moved the stack upwards. Yeah, because you've done that in P3B, we will not let you do the same thing again here. So yeah, that's why we provide you the new base code. You can just start adding more stacks downwards, basically. Yeah. Okay, so for now, let's take a look at the base code. So okay, again, the reason why this part is easier than P3B is that okay, the first reason is that you have done some horrible things in P3B, so you have gained some experience. That's one point. But another point, which is more important to make it easier, is that for P3B, you are basically modifying the whole memory layout, right? Moving things up and putting the stack upward. But for this part, you actually don't modify the base code. I mean, no, you don't modify the memory layout of the base code. You just add things to that memory layout. So simply appending or adding things to that will less likely to make your kernel panic. Instead, if you like moving things, updating the memory layout, it's very likely that it's kernel panic. So that's one of the reasons why this looks simpler or easier to debug. Another thing is that, yes, you can remember in P3B, you have to modify a couple of places, right? vm.c, proc.c, and exec.c. syscall.c, something like that, trap.c. But for this part, I think most things like kernel thread implementation, like the clone method, join method, and also the second part, which is like the condition variable implementations. All this happen here in proc.c. So you just add new method in this in proc.c, and that's it. You don't need to specifically modify some existing code. Oh, probably not at all, but probably not at all. I mean, you have to still change something like in fork and wait. Yeah, I'll talk about that later. But the main job, your main workload will be basically focused on the adding the new method you wrote in this code. Okay, so
now when we add these, since we're adding system calls, we have to add them to all the locations we always add a system.
Exactly, but you've done that many times, so yeah. But I mean, the core or the major real thing happened here. Yeah. Okay, so how are we gonna start implementing clone or create a thread? So let's just take a look at our old friend fork. So in fork, so can anyone tell me what's the difference between fork or more generally, what's the difference between process and thread?
Process, you create a new process. In thread, you have the same process and code and all that. You just create a new based on the code in the address space.
Exactly. Yeah, address space. So the major difference is that for a process, each new process has got its own address space, right? But for thread, they're sharing the well, not the entire address space, but like the heap and code in the address space. They have their own stack, right? So then one major difference between fork and clone is that so in fork, where do we? Oops. Oh, 6 o'clock, right? Yeah, yeah. So I have to wait for a couple several minutes. Yeah, it's the system shutting down. Okay. Yeah. We don't need that much. So for fork, we basically create a new address space for every new process. What method do we explicitly call in fork to do this thing? Can you remember that? Based on P3B.
Alloc UVM.
Exactly, copy UVM, right? So creating a new process or forking a new process is essentially copying the address space from the parent. So we call copy UVM in fork. You can take a you can also open the base code. But anyway, it's so when we do copy UVM, we basically copy the address space. Here is like the page directory to the from the parent. Okay, but in clone, right, we will not do that. Right? We don't copy the address space. Instead, what we do?
Copy the stack to our stack? Or do we
Yeah, we copy the stack. Okay.
to a new page?
Right. That's one thing we should do. What about the heap and code?
Just need to create a reference to this.
Exactly. Yeah, we don't copy it. We just create a new reference to that. That's the major difference for fork and clone. This is for the address space. Should we video control turn it on? Okay, let's turn it up. Okay, so yeah, I think I better combine this to talk about. Let's take like 1 minute break. Yeah, what did I do? So I select HDMI and then send to screen.
Yeah.
Okay, gotcha. Yeah. Okay. Okay, so yeah, this is like in fork we do the copy UVM, right? But now in clone we don't do that. Instead, we just have a new reference pointing to the same page directory. But meanwhile, that's we have to maintain a new stack, right, for each thread because each thread has its own stack. And in clone, we will basically create the stack at the corresponding location, right? So that at the correct location, you have to make sure that when you create a new stack, you have to carefully manipulate the boundary here. Make sure that you have a guard page here, right? Creating a stack is easy, right? You just call alloc UVM, right? And then that's it. Okay, and then like this is copy the size, which is the same, I assume. Okay, so here for clone, you essentially, yeah, this should be also the same. So basically, when a process clones a thread, the thread's parent should be that process. Okay, so this should be the same. And I think this is probably different than the implementation of the real Linux kernel, but I'm not 100% sure. Is that although we so-called create a kernel thread, but it's still kind of like a hacking thing here. The reason is that in terms of scheduler, okay, so if you still remember scheduler, when you do like a multi-level feedback queue scheduler, you interact a lot with the p table, right? So after you clone a new thread, you should basically also put that thread into one of the entry of the p table. So in terms of scheduler, or from the perspective of scheduler, the thread and the process should be no difference. They should be the same, as long as the scheduler can see, right? They're just placed into the p table, and every time you do the schedule, you schedule whatever is in that entry. So for scheduler, it doesn't see any difference between the process and the thread. Okay, that's a clarification. So you can easily use also allprog. Behind allprog, you create a new entry in the p table and store everything PCB there. That should be the same. And here is just copy a bunch of file descriptors. It should be the same. Okay, but that's not it for clone. What else do we miss? Yeah, probably it's too general. I mean, not very obvious from looking at the code. But
check to make sure we don't have more than 8.
Well, yeah, that's kind of like boundary checking. It's not, yeah, and I'm not asking for this. So if you look, sorry, if you take a look at what clone is used, what arguments are passed into clone. Okay, so the prototype of clone looks like this: 2 arguments, a function pointer, and another like argument pointer. What are these 2 guys? Because in fork, you can remember it doesn't take any argument, right? Just fork parentheses. But in clone, we have these 2. How are we gonna deal with this? What are these doing? Why do we need these 2 guys? Any ideas? So if you could remember, let me open again Ramsey's book. I think he's got Threads API.
The function pointer at the start of the code.
Exactly. So let's take a look at the Linux thread. Okay. So essentially, pthread create is very similar to clone here. Okay. Clone is a system call, but this pthread create is like a user library. It essentially calls clone to some extent. But let's take a look at the pthread create. It has got multiple arguments, but the key argument are just two. One is excuse me, this one, the start routine, right? You see, very familiar with the func, right? It's actually a function pointer. The next one is the argument. The argument is actually the argument of this start routine. So basically, every time you create a new thread, before you create this new thread, you have to define the start routine, right? In this start routine, you basically it's a function, normal function, where you do the real thing that you want this thread does. You want this thread to do, right? So likewise, for clone, you should you should essentially sorry, I should look at this one. Yeah, if you want to use clone, you have to create write a function, and then you feed in this function pointer to clone. Okay. So the tricky thing is, how are we gonna so we pass into the function pointer into clone. How does clone know, okay, now I want to run this method, this start routine?
Our instruction pointer to...
Yeah, something to do with that. And does it look very similar to something we've seen before? Come on, you can think of it.
Or you can do it.
Oh yeah, okay, sure. Okay, yeah, exact. Okay, so I think you've read a couple of, you've been working with these guys a long time in P3B, right? I think you should be very familiar with that. Exactly. So so it's very like exec, and so as you can remember, in this exec we create a stack, right? And then we push the arguments into the stack. And also push the fake return address there, FFF. And then point the EIP to the main, right? And that's it. So here in clone, similarly, we should basically populate this argument, populate the stack you created with this argument. And then you set up like the ESP, EIP. The EIP, he said correctly, EIP will point to this the function pointer, right? And then you're ready to go. So technically speaking, a clone system call is just like the combination of fork and exec for a thread. So for a process, we separate these two. Fork is fork and exec is exec. But for clone, right? So you first create a new thread by having a new address space pointer, which is the page directory pointer pointing to the parent. And then you do a couple of copies, not the address space, but a couple of other like registers copying the file descriptors. And then you create a new stack. This is actually happening similarly in exec, right? Create a new stack, and then populate the stack with the arguments, and then set up the registers, and then finally the EIP pointing to the func pointer, and also the return address set it to the EFF, the fake address. and that's it. So this is what clone does. Yeah, basically fork plus exec. Okay. And what about join? What does join do in the thread? Right, basically, so I mean, when you create a new thread, you set up the stack, right? And then the function, the start routine will automatically run. And join is an API which handles to first clean up the corresponding the thread, and then it makes sure that after you do the join, it's kind of like waiting the process to waiting that thread to finish, right? So join is very similar to wait here, right? So wait is still remember when you call fork at the end you call wait, such that you would do make sure that the order of the parent and child process. So similarly for join, we make sure that the main thread, the order of the main thread and the newly created thread, the orders. So let's take a look at what wait does. Okay, so it's like a forever loop, and each loop it scans through the p table, right? And it looks for current process if proc is current process, the calling process. Okay, if the calling process has the same parent as this the entry in the p table, if it is, then I say okay, I found the parent of process of the current process, and then oh sorry, I said it reversely. So if a p dot parent is the same with proc, then I'm saying the process P's parent is this guy. So which means we found the child, and then we will what we will do next. We basically set this state to zombie state. Okay, we found one, and then we do k-free. So also k-free is fine. Yeah, the free UVM. I think it's kind of the opposite of copy UVM or L UVM. So it basically just free the address space because this process has been set to zombie, right? It's been finished. So we will free the address space. However, if we want to implement join, will we do similar thing here? No, right? Because we don't want to free this address space. The reason is that it's just a reference, right? If we free this address space, then what about other non-terminated threads that share the same address space? Right? We have to make sure that if this address space is no longer referenced, then we should free it, but not at every instance of join. Okay, so here you should be very careful when you implement join. Other than that, everything should be similar. Okay, if we don't have any children, then we just release the lockup p table, right? Okay. This is for join.
So I'm just trying to make sure I understand what join will do. So we only want to clean up that thread's sort of page of the stack. If any thread that's using that page is terminated.
So every time you call join, I think join returns the value of the PID that's being killed, right? So
No, it returns value. Oh no, I'm sorry. You're right. Yes.
right. So basically, it can technically happen any. I mean, as long as it satisfies the criteria, then it will select that process thread and then set it to zombie state. So say, yeah. So if you have a process that creates multiple threads, right? So this is the main thread. Now it's not full, but no. Three threads, right? T1, T2, T3. And it's, remember, it's the main thread that is calling join, right?
Okay.
It's called
And just so I'm clear,
by name.
there's one virtual address space that's shared by all of these, but then each thread has its own page allocated for its stack.
Right, exactly.
Okay.
So when main calls join once only,
Yeah.
potentially it can kill any of them,
Right.
but just one.
Yeah.
Say 2, okay, because 2 is the child of node, right? So when called join, it can wait for T2. So if we want to wait all of them, we should basically every time we just kill one, and the one we kill will be returned as a thread.
What I'm trying to struggle with is, and maybe I'm making it overly complicated. So you have the stack in the virtual address space, which we know can be there can be 8 simultaneous threads because there's only room for 8 pages. Mm-hmm. And as a thread is done and it joined, we have to use that page again for a future thread.
Exactly.
So we have to know when it's available for. So I guess I'm asking, one, do we have to implement some sort of memory tracking thing so we know which pages
Yes,
are available?
you're correct. Yeah, I think I forgot to mention.
When do we know that it's free? When it's joined, we can use that page again. Is that always true? Or if T3 was actually referencing something on T2's page, which it said was okay in the instructions, do we have to wait for T3 to be done before we free up T2's page? Because I don't know how that would be known.
So you mean, do we say something like this is possible?
I thought it said that in the instructions. Thread A may directly dereference the address in thread B's stack. It's the second bullet in italics.
Okay, in your implementation, thread A may directly dereference. Oh, this is saying. Okay.
So I was trying to understand, because that means that T3 could be dereferencing something in T2's stack, right? And then join gets called and T2 is gone. I clear up that page because I'm going to reuse it for T9.
Okay, yeah.
But then T3 is still referencing something that's now in a totally different stack.
I think you don't need to care about this. I mean, so basically, so this reference, so the italic here is, I mean, so as you can
we go
remember.
back to the crossed out part? Because that seems like better.
Sorry?
The crossed out bullet point sounds easier because we implemented that.
Okay. So the stack of thread A should be. Well, this will be an issue because let's see why it's crossed out.
If you reverse A and B, bullet point 3 sounds possible because you're copying. You start by copying the stack, where copying the stack is fine because they're both at the same point in the stack. But with the order that it's written in, it sounds absurd.
Well,
I think the reason why we say this is that so you create a thread A, and in this A you dereference. You have a pointer whose address is pointing at B's stack, but somehow B is also allocated, and then there's no error raised. But if B is somehow finished and join cleans up the stack of B, then which means this page of stack is no longer mapped. So when A at this time tries to dereference the address in this unmapped address, then we'll raise a page fault.
so we should page fault if there's any reference references to an unmapped boundary page in between stacks, right? Because you have those. Like,
You don't need to do that yourself. I think
It'll
it's
just
done
automatically.
automatically.
But and then if there's a page that we haven't allocated because that haven't gotten there yet in sort of growing process pages, and there's a reference to it, that whole page falls because those aren't allocated.
Right.
And then after we clean one up, it should return to that behavior, even though it might have been able to reference it while that was running.
So basically, every time you join, you clean up this thread. You also unallocate that.
Unallocate that. Okay.
Right.
But if you allocate a new one, it's a valid address again.
Yeah, but before you do the new one, it's unallocated.
So you could have this weird behavior
Yeah.
where T3 references an address in T2 space while T2 is running, and it works because T2 is running.
Uh-huh.
T2 is joined and goes away, and T9 is put onto that page, and then T3 goes to the same address again, which is now in T9's space, and it works again, even though it's a totally different thing now, because
And that's okay.
That's okay.
our
All
users
right.
should just not write programs that do that.
Yeah.
Okay.
Okay. Yeah. It's okay.
And so then we do need some sort of data structure to track
Exactly. Yeah, that's what was
stack
gonna.
pages. Okay.
Yeah.
That's what I thought, but I wanted to confirm.
So it's for this, particular this part is also like P3A, right? You have the shared memory page. You have 64 clients, and here you have 8 threads that is doing things here. So every time a new thread, the old thread is joined, then that stack should be unallocated. So then you have to maintain the record or another data structure to keep track of which page is allocated, which is not, so that you can allocate a new thread at that free or unallocated page. Okay.
Well, can you just look at the page table entry and see if it's marked as present or not?
Yeah, you can do that. I didn't try that. So in terms of my own implementation, I maintain my own data structure to keep track of that. But I'm not sure if that works. It sounds working, but I mean, yeah, you can try that. But yeah. Okay, so
Well, I
join.
guess it depends on whether you're track which thread it was. Because if you follow a UCOM that's allocated, you can go on to any number of threads. So if you have to care about which thread it is, then you need your own memory space. But if you don't have to care about which thread it is, then whether or not it's allocated should be valid.
Well, the process, while the thread is active, you would know what page it's pointing
Well,
to
that's also valid.
in the proc struct. And once you kill that, you don't care anymore.
Right.
So I think his method would work. It's just, I think I'm really just gonna do it.
Yeah, yeah, that's what I did. Okay, so this is for the first part of P4B, which is the thread implementation. After that, you'll try to create logs, right? And some other some other APIs like the condition variable and the semaphore as a second part. So I think creating a log is very straightforward because for this project, we only need to implement a Spring log, right? You've done that in class and worksheets. And also there's some example in XV6 as well as in kernel, there are some log. You can take a look, which is I think it's at spin log. Yeah, here is like a log initialization and acquire release. So it's like a kernel log. Yeah, the familiar exchange atomic hardware instruction here. So what you do is create a user library so that user can use the log. So, but for lock, it's very easy. The main thing I want to focus is on the condition variables. Okay, so for condition variables implementation, so again, condition variables, because if you can recall, we basically will, especially in wait, right? Count wait, we will put a caller to sleep. And the best way to put caller into sleep in XV6 is to call like yield, right? Or like SCAD, if you can remember. But these are all like in kernel space. So the easiest way to implement user level condition variables is to create a system call for like a condition wait and condition signal or even condition init as a system call, right? The reason is that we have to put the caller to sleep. That's happening in kernel, so I think it's more convenient to do that in kernel. So you have to create a bunch of system calls. Okay, so for condition variables, I think you have to, because if you can remember, the fundamental piece for condition variable is a queue of process that is sleeping, right? So let's open, I think it's CV. Oops. Okay, the wait call is executed when a thread wishes to put itself to sleep. It doesn't say full things. Never mind. Yeah, I think you can recall. So for count wait, you basically first assume you have acquired the lock, right? And next step is put the caller to sleep and release the lock. These two steps should happen atomically. And third step is wait until you regain the lock, right? This is the 3 steps for count wait. So for the middle step, you have to put the caller to sleep and release the lock atomically. So for this to ensure this atomicity, you have to have another lock, right, to protect this critical section. This lock is actually explicitly protecting the queue of condition variable. So in your condition variable data structure, you have to also have another lock to protect this queue. Speaking of the queue, definitely should maintain your own queue in this condition variable data structures.
Queue part of the user function, or is that something we would do in the kernel?
It's in the kernel. The user it's invisible to the user.
So the user would just have access to call the functions.
So the user is just it only has access to wait, count, and count wait and count signal and count init.
Okay.
Yeah. The CV, the data structure in CV is not visible to the user. Yeah.
Okay.
So I think the best way to have to implement a queue is definitely not a linked list, although it's okay to do that. So my suggestion is create a static array. I think it should be straightforward, but I think I should mention that let's do this conflict a bit more fancy data structures. So you have basically some CV data structure. You have first have a lock, right, to protect this queue, and another queue, which is a static array. Okay, so what will we store into this array? So we basically put the caller to sleep. Right? And that's when we put something into the queue. What is that? Yeah, so basically put something, the information of the process that's put into sleep. So what's best to put into sleep? Like the whole PCB, but that's too exactly a bunch of pointers. So when a color is put to sleep, then you just put the pointer of that color into the queue. And such that when you do like a count signal, right? In count signal, you will so in count signal, you will wake up one thread, right? Only one, not broadcast, only one thread. So which to wake up? You just look through the queue, and because it's queue, then it's first in, first out, then you just wake up whichever is the first. You just queue of the first element, and which is the clock. And then this is the process you want to wake up. So then you will do clock state ready. Something like that. Okay, I will talk about this more in more details later, but right now let's focus on the data structures of Q. So I said it's best way to do that in a static array. But if you can remember, we can add things easily at the end. But when we pop the process from the queue, then how are we going to maintain this? Removing element is it's not very good for static array. Always you have to shift. Right? So the best thing to do is to have a static array which is circular. This is the most convenient way to do. And then you have to maintain two more pointers, the head pointer and the tail pointer. So the reason is that, so you have let's say we have 8, because we have at most 8 vectors. So you can safely just allocate 8 entries for this static array. That's why you don't need 64. 8 is enough. And now, right now, for instance, your head is here, the tail is here, right? Then essentially, how many elements are there? So the size is 5, right? So every time you enqueue, you basically just increment this tail. When you enqueue, you increment this tail and put new stuff here. And every time you dequeue, you just increment the head. So you just maintain these 2 pointers. There's no need for you to like shift the overall view. No need to do that. It's like, this is the best way. And what about if tail is at the last element? What do we do when we increment this tail? And then not exactly, just wrap around, right? Here. And that's why it's circular. It's just wrap it. So this is the data structure. I think the best way to do that. The static array to increase Q. Okay. And then let's take a look at how are we gonna implement count weight and count signal in details. So again, like a fork, you can learn, like clone, you can learn from fork plus exec, and join, you can learn from wait. There's still some thing for count wait and count signal you can look at, which is sleep and wake up. So for sleep, it's very similar to count wait. Let's see what sleep does here. So here are a bunch of checkings. Okay, you can see sleep takes 2 arguments, right? One is the lock. Okay, that's fine. The other is kind of like a pointer called chan. I think it's short for channel. So it's like the CV we have, but for this chan, it's just like a single pointer. But for our CV, it's got a data structure, right? It's got a lock in it, and it's got a queue, and you have to maintain the tail and head. But for sleep, it's simple. It's just a pointer. And you can see here. Here is just a bunch of check-ins, and here you go to sleep, right? You just put this. You just remember or record this this pointer to the PCB of this process, and then put it to sleep. And SCAD is yield, right? SCAD internally calls yield and relinquish the CPU. And after that, you will reacquire the original lock, right? So it's the same with the last step of the count wait. Even for the first step, here, you have to assume that lock is 0. Oh, sorry, lock is 1. Lock is 1 means you have acquired the lock, right? Otherwise, you will panic. So for count wait, similarly, you will first assume that you have already acquired the lock. So this cannot be 0, it should be 1. And so for count wait, instead of simply updating the channel, you will basically just put the proc pointer to your in-queue it into your queue. Basically just in-queue that proc pointer. Okay. Another tricky thing is that you have to make sure that it happens atomically. Yeah, that's why you have the lock inside the condition variable to keep it atomic. Remember, the lock in the CV data structure is different from the lock we passed here. Okay, so they are different. So don't be confused. Because just remember, so count wait takes 2 arguments, right? One is the CV data structure. The other is the lock. That lock is defined by the user. It's to protect. Yeah, in CV model you have a lot of. Skip that, but that lock is different. That purpose is absolutely different from the lock inside the data structure of CV. The lock inside of the data structure of CV is just to protect the queue in the CV, to make sure that put the caller to sleep plus release this lock atomically. Okay, looks confusing, but you have to make sure that these two are distinct. Okay, for count signal, it's simpler. It's resembling wake up. So for wake up, you can see just loop through the P table and find whatever is sleeping and matching the channel and then put it to runnable. For count signal, you just pop the queue, right? You dequeue, get the pointer of the proc, and then just wake up that proc by setting the state to ready. That's it. Okay. As for semaphore, so we've learned that we can create a semaphore from a lock and a CV, right? Since you have implemented lock and a CV, then semaphore is like trivial thing to do. Okay. So the challenge here is just the CV, how to maintain the queue in the data structure. Okay, I think that's it. Any questions?
Can we post these online?
Sorry?
These videos online?
Yeah, definitely. Okay, and let's call it a day.